Okay, in principle, we can start. So the first talk will be given by Ilya Kondratyev. The title is Semi-Implicit Multidimensional Unstructured Gas Dynamic Solver for Astrophysical Applications. Please, Ilya, share the screen.
Good morning, dear conference participants. Can you hear me?
Yes, we can. Please.
Do you see my presentation as well?
Yes, we do.
Great. So, good morning, dear conference participants. My topic is devoted to semi-implicit multidimensional unstructured solver for gas dynamics with self-gravity on unstructured grids. I work with collaboration with Dr. Sergei Moisenko in Space Research Institute of Russian Academy of Sciences. So here is an outline of my talk. After short introduction, I'm going to tell you about the support operators method and the derivation of difference analogs of differential operators in 3 dimensions. And after that, I'm going to tell you about the application of this technique to construct a semi-implicit scheme for gravitational gas dynamics. And further, I show you some test computations. The most of the codes, the most of the astrophysical codes are based on the explicit solvers. And it is well known that all these explicit solvers are only conditionally stable. There is a so-called current Friedrichs Levy condition, or CFL condition, which tells us that the fastest wave in the system shouldn't propagate further than the minimal cell size during the time step. So, and here are some examples of the CFL condition. This one is for the explicit scheme for the gas dynamical equation, for the heat transfer, for the explicit scheme for the heat transfer equation, and for the advection equation. And the restriction for the type step, as it is also well known, is that CFL parameter should be less than unity. But in some cases, implicit or semi-implicit schemes may outperform the explicit ones. So traditionally, the heat transfer equation is solved implicitly due to very restrictive condition for the explicit scheme. It stands also for gas dynamics with dissipation and multi-phase flows. And also recently it was shown that the stellar evolution calculations with the implicit code also outperform the explicit ones. But we're interested in a bit different types of flows, which are very common for astrophysics. These are the flows with a wide range of local Mach numbers, from m much less than unity to m much more than unity. So at the same time, we have the presence of dense objects with high sound speed and at least incompressible regime of the flow. While in other part of the computational domain, we have a compressible regime and possibility of strong shocks and other fluid discontinuities. So, and here are some typical astrophysical examples, and all these kind of flows have a common feature. So here is an example of such kind of simulation. Here is a 3D MHD simulation of magnetic-rotational supernova by Möster and his colleagues. And here we can see a very compact, dense object, collapsed object. It's a proto-neutron star. And here is, it has very high sound speed. While in other part of the computational domain, we have a compressible regime, and you can see some discontinuities, shocks, and so on. So, and the main restriction, which comes to the time step, is due to the acoustic installations of this central compact object. So, if we treat these acoustic installations implicitly, there is a hope that we will increase the performance of such kind of simulations. So, and to construct a semi-implicit solver, we use a three-dimensional extension of the support operators method. So the basic idea of this method is that the difference analogs of differential operators should be derived in the way to satisfy the same identities as the continuous operators. So for example, we have the divergence operator, which is conjugated to the gradient operator. The curl of a gradient is exactly 0, and so on. Also, this method allows to use unstructured mesh, so we have no allocated direction. In our calculations, we use tetrahedral mesh in 3 dimensions and triangular ones in 2D. Also, usage of unstructured mesh allows to use static mesh refinement automatically for free. And also, it is very useful property that the Laplace operator transforms into a symmetric and sign-definite matrix. So it can be easily reversed by fast conjugate gradient method and so on. So also in our group, this approach was used to construct a completely conservative operator difference scheme in Lagrange variables for two-dimensional MHD flows with self-gravity, and it was applied to the problems of magnetic-rotational supernova explosions. So, and on this slide, you can see the list of operations which are needed to construct the pair of conjugated difference operators. So, first of all, we should define some linear mesh spaces. For example, the spaces of nodal functions, of cell functions, and so on. And we built the difference operators in pairs. So here is an example of the gradient and divergence operators. So the first operator is obtained using any numerical differentiation technique. And the second one is evaluated from the difference analog of the green formula. Here it is for the infinite space, which should be written in terms of mesh scalar product. And by substituting the gradient operator in the analog of the green formula here, and rearranging the terms, we can derive the divergence operator, which is conjugated to initial gradient operator. And the same technique can be used to the whole set of vector calculus operators in any geometry. So this approach was proposed by Zlian, Kosmachevsky, and Chernigovsky in 80s. And also they have derived the so-called boundary operator, which is analog for derivative in the boundary nodes. And it satisfies the green formula with the boundary. And for Lagrange calculations, Lagrangian calculation, it allows to include boundary conditions in second and third types in the operator difference form of the solving problem. And here are the derived operators for the nodal approach. So the operators transform the function from the nodal space also to the nodal space, and they can be obtained using piecewise linear finite element basis functions on a triangular in 2 dimensions or tetrahedral Delaunay grid in 3 dimensions. For 2 dimensions, it was done by Zlian and Sablin. And also, it can be used a piecewise constant finite volume approach on median dual mesh, as was done by Timothy Bard. And it should be noted that these two operators are conjugated to each other. So also so-called cell node approximations can be used. In the case of cell node approximation, the Laplace operator has a more compact stencil, which may be efficient for the parallel calculations. So so some functions are defined in the cells, while the other functions are defined in the nodes of the domain, of the mesh, sorry. And here is the approximation of the gradient operator, which transforms functions from nodes to the gradient function of the function in the cells. And the divergence operator, which transforms function from cells to nodes. So, and it also should be derived with the analog of the green formula in the cell nodal space. So here is an example of cell nodal operators application in 3 dimensions. So we have solved stationary heat transfer equation with entropic thermal conductivity in outer layers of a magnetized neutron star. So here is the original differential boundary value problem, and here is an operator difference boundary value problem. So this is an example of the surface temperature distribution of a neutron star with magnetic field, and here is the synthesized light curve, including the effect of general relativity. But now we're interested in gas dynamics with self-gravity. Here is the system of the equation written in conservative form. We restrict ourselves in Newtonian approach. So we can use the methods for low Mach number Navier-Stokes equation to build a so-called all Mach number solver, which treats only acoustic waves implicitly. And it was shown by Kazuli and Greenspan that for the case of compressible flow, only pressure in the momentum equation and momentum in energy equation should be treated implicitly. And they used the staggered grids to obtain monotonic solution in the incompressible limit, but we have also built the scheme on a collocated mesh with nodal difference operators and found no oscillations as well as in the paper of Cardier et al. So here is some implicit approximation of our gas dynamical system. The pressure here is implicit and momentum here is implicit as well. And to approach to a second order in space, we use a linear reconstruction of conservative variables, as in Godunov type methods, with but Jefferson slope limiters here, here, and here. So to obtain monotonic flow profiles, we use Rosanov type dissipation, which only depends on the flow velocity, but not on the speed of sound like in Godunov type methods. So and by substituting the momentum from here to the energy equation, we can obtain a nonlinear elliptic equation for pressure. That's it. And it can be solved iteratively by a Newton type method. We use Picard iteration plus linear solver on each Picard iteration, as was done by Dumser and Kazuli, and later by Kazuli and Zanolli. And the usage of support operators technique allows to construct a matrix with good properties. So it's a Poisson-like equation. So here is the Laplace operator, and here is the diagonal term. So, and the stability condition of the scheme is much milder than the usual CFL condition for the explicit solver, and it depends only on the flow velocity and not on the speed of sound. So here are some test calculations. We currently we use only low resolution meshes because we don't have yet a massively parallel version of our code. So here is the Sochok tube calculation and its comparison to 1D IHL calculation. And it was found that the method is about 3-4 times slower than the explicit scheme for the shock tube calculations. And further, we have tested our method with strong shocks and simulated the Sidov-Taylor blast wave and at large time. And also, if we if we refine the mesh near the center, as usually done for the supernova, for example, calculations, this simple problem, in some sense, emulate a situation of the interest when we have very, very high sound speed in the center, while the flow velocity in the center is at least 0. So that at larger times for three-dimensional set of Taylor blast wave calculations, we have found that the advective time step can be up to several hundred CFL time step, while the solution is still monotonic and stable and agrees well with analytical solutions also. So after that, we have tested the scheme in low Mach number regime. So we have simulated slowly moving contact discontinuity, and it was found that semi-implicit scheme is about 50 times faster than the explicit solver, while the flow profile has a better quality due to low numerical dissipation, which depends only on the flow velocity. So after that, we have tested the Poisson solver to include the self-gravity in our calculations. So here is the operator difference problem for the Dirichlet boundary value problem for the Poisson equation. And here are the comparison of our simulation with the analytical solution. Finally, we have tested the scheme in the regime of the gas dynamics with self-gravity. So we used a low-resolution mesh, and at not very large time, the dust collapse without the pressure agrees well with analytical solution, while at larger times we have a low-resolution mesh and calculations don't agree well. So that's all. In conclusion, I may say that we have constructed a three-dimensional semi-implicit operator difference gas dynamical solver, which treats acoustic waves implicitly, and it is efficient enough to treat both high and low Mach number flow at the same time. So, and we plan to extend the scheme to second order in time and use so-called implicit-explicit Runge-Kutta methods. And also plan to develop a massively parallel MHD version of this code for studying multi-rotational processes in rotating protostellar clouds and cold collapse supernovae. So thank you for your attention.
Okay, thank you, Ilya. Please, questions, comments? While the audience is thinking, I'd like to comment. A few slides before the final slide, you wrote that we've got the gain of 50 times.
Yes.
Corresponding to the explicit solver. But this a little bit not strong point. I mean that we can say exactly, or more or less exactly, that the game is 50 times or 30 times or 100 times.
Sure. Only on this problem, actually. And also, we have some advantage in sort of Taylor calculation also, but it's not actually 50 times, but there are some problems that can give us such advantage.
That's right. I just want to say that if we consider here is just one-dimensional problem, but if we consider multi-dimensional problems, it's important to it's nonlinear processes. It's important to compare it on a large grids of large dimensions. Only at this point we can get a real gain. Other questions, please? Comments? Okay, if no questions, no comments, I'd like to ask Ilya to stop sharing his screen. And the next talk will be given by Tisher Mondal, ultraluminous X-ray sources as magnetically powered advective flows around stellar mass black holes. Please. Okay.
Hello,
We
am
hear
I
you and
audible?
yes, we hear you and see your presentation. Please
Okay.
start.
Okay, good morning, everyone, and thanks, Professor Moisenko, for giving me this opportunity. And I will talk about ultraluminous X-ray sources as magnetically powered advective flows around stellar mass black hole. And this project has done with Professor Mukhopadhyay at IISc. So here is a schematic diagram, which basically telling that one X-ray binary where black hole is sitting at the center of this disk, and this is companion star, and mass is supplying from this companion star. And at the same time, since it has angular momentum, matter cannot fall directly to the center of the black hole. It rotates and spiral down and form the disk-like structure. And at the same time, huge gravitational potential of the black hole will convert to heat or radiation, and we sometimes see very powerful jet. And the efficiency of conversion from gravity to heat or radiation, it depends on the spin parameter of the black hole. And if we compare this energy budget with the nuclear fusion reaction from hydrogen to helium, so this is much more powerful than the nuclear fusion reaction what is happening in the star. So black hole accretion is very powerful source of energy, and it controls basically by these four parameters. One is mass and spin of the black hole. One is that mass accretion rate from the companion star, and the magnetic field strength and geometry in the disk, and the radiation mechanism. So one such example is that ultraluminous X-ray sources, which are very bright off nuclear point sources with apparent luminosity in the range of 3 × 10⁻³ to 10⁻41 arc per second. So this range is basically higher than the higher of the Eddington limit of a 10 solar mass black hole. So to explain large luminosity from this stellar mass black hole, if we consider from basic Newtonian physics, you can see that it is proportional, luminosity is proportional to the black hole mass, and also it proportional to the mass accretion rate, at which rate from companion star mass is supplying. So by basic three mechanism, the large luminosity can be explained if mass is higher, like intermediate mass black hole, when m dot is low, like Semi-Implicit accretion rate. As I go along, I will discuss about what is Semi-Implicit accretion rate and what is the role of intermediate mass black hole phenomenon. At the same time, we can take M is the stellar mass black hole, but M dot is high, like super-Eddington accretion phenomena. Or third scenario, we can see as a beam emission of the apparent luminosity. So for stellar mass black hole, for beam emission, we can see large luminosity. So to get physics about different kind of accretion phenomena, we have to look about accretion unification scheme, which is depends on the mass accretion rate, which is written in unit of Eddington unit. So Eddington unit, basically a star can give maximum luminosity where outward radiation pressure is balancing by the inward gravity. So one means accretion rate is 1 Eddington unit. So I will discuss every disk model based on the standard disk model because it is the most familiar disk mechanism. So what happens when this accretion rate is in this zone? So matter density is comparatively high. That means ion and electron in this disk is comparatively high. So whatever heat will generate, it initially goes to ion because of its heavier mass. And since high density, ion can easily transfer the dissipated heat to electron, and electron can radiate it out. So whatever heat will generate, it will dissipate it out. That's why it becomes very thin disk-like structure. And observationally, we see high means high luminosity and soft photon like black body multicolor disk black body type spectra. When the accretion rate is low, that means matter density is low, so ion electron coupling will be low. So whatever heat will generate, it will resides in the ion. It cannot transfer to electron very easily. So that's why the heat becomes stored as entropy, and this become very hot and puffed up. So it's like quasi-spherical type structure, and it's known as advective type of accretion flow. And in this accretion, because of advection, large-scale strong magnetic field also advection happening, and we see very powerful jets sometimes. So the observationally, we see very low luminous, and hard means photon energy is hard. So this is fitted by power law spectrum where hard photon index can be vary from 1.4 to 1.8. Quiescent state is the lower version of this low hard state when accretion rate is very, very low. So that this become very, very faint, and we can see the information of the optical emission of the companion star from this state. So that's why it is also important. But the things will be completely different when accretion rate will be very high, like 1 or greater than 1 Eddington unit. So this is known as slim disk model. So the disk densities will be very high. So whatever heat will generate, we can expect it can radiate out, but because of high density, radiation cannot come out, and it is known as photon trapping. So some percentage of the photon will be thermalized, and some percentage will be giving the power law type spectrum. That's why it's known as very high state or steep power law type state. But photon index will be higher compared to this state. The second important parameter is that mass of the black hole. So it can be stellar mass or intermediate mass black hole to explain large luminosity. So one scenario is that accretion rate should be high to explain large luminosity, when black hole mass should be stellar mass black hole. But if the accretion rate is low in this state, if we see observationally in this region, then stellar mass black hole cannot explain that ULX large luminosity. So we have to take intermediate mass black hole scenario. So intermediate mass black hole scenario comes once this is luminosity versus temperature plot. So not only for large luminosity, also the disk temperature become cooler. So as we know from Keplerian standard disk, the temperature of that disk inversely proportional to the black hole mass. So that means when the cool disk temperature can be explained by large mass, and at the same time it can give large luminosity. So this is one of the stellar mass black hole candidate, and here the intermediate mass black hole scenario is stepped. But the problem is the ULX spectra, it does not fit with only that Keplerian type disk. So if we feed this Keplerian disk plus power law model, it's modified this cool disk model transferred to this high disk hot disk region. So here this luminosity versus temperature plot, and this is stellar mass black hole is sitting here, and intermediate mass black hole if we feed with only cooler disk. And this is the Eddington luminosity. You can see that large luminosity also can be explained by stellar mass black hole when accretion rate should be higher. So in this case, the whatever cool disk can be explained by the disk corona coupling model, where hot corona will extract the heat of the disk. Also, if we feed the power law, depending on the fitting range, the soft excess can be soft deficit depending on the power law fitting. So in this way, the intermediate mass black hole scenario had been disputed extensively in this work, in various work, and it is well accepted by the superintendent accretion with stellar mass black hole to explain the large luminosity. But there are some interesting sources, very rare. Out of 300 sources, there are around 10 sources which photon index is very low. That means hard state, and luminosity also very high. At the same time, keeping this photon index low, the luminosity also varying 1 order larger. So that means superintendent accretion cannot be applicable for these sources. So some alternate mechanism is required. So to explain this, so we can see in this zone, this is coming observationally. Instead of low, this is like bright hard state type spectra. So we want to model in this zone. So for that, we have to take care about that magnetic field advection, and that accretion rate should be low, and we take care stellar mass black hole only. So what is the role of magnetic field here? So magnetic field basically will play a role in two ways. When magnetic field is weak, that means it can be like MRI, magnetorotational instability, where that angular momentum transport happening by weak magnetic field. So this is one schematic diagram of spring mass analog of MRI, where the spring is basically playing the role of weak magnetic field, and it is connected by two blobs. So if you part up the system, that inner particle will disturb and face the forward torque because of large velocity. So it will lose some angular momentum, and the outer particle will gain the angular momentum. So outer particle will move, take the angular momentum outward, and inner particle will slow down to the black hole. But the situation is different when the MRI mechanism is not applicable for like non-ionized medium, or if magnetic field is very strong. So then it will not operate like a spring, it can behave like a strong rod. So at that time, the magnetically dominated accretion flow can be divided in different mechanisms. One is magnetically arrested disk model, where large-scale vertical poloidal field can be accreted from the outside medium or companion star. So it is originally proposed by the Bismuth Kogan in 1974, and then developed by Narayan 2003 and later on. So there are other kind of accretion disk model where the radial and toroidal field also can be advection possible. So we take care of all this kind of mechanism and try to model theoretically disk outflow couple model. This is nothing but conservation of mass, momentum, and energy equation. So first term is basically radial mass flux, and the second term is that outward mass flux. This is momentum balance equation. So first term basically taking care about that advection and centrifugal force. So F is that force due to black hole gravity. Here we took pseudo-Newtonian framework. And this is pressure gradient, and magnetic field has dual nature. One is pressure gradient, which is behave like a isotropic pressure, and other is magnetic tension like term. So if you extract the rubber band, it will give some negative pressure. And W is the turbulent mechanism, where the W is basically taking care of turbulent flow, and alpha viscosity parameter we will written down W in terms of alpha viscosity parameter. So the pseudo-Newtonian framework we use for non-spinning black hole Pachern-Squita potential, and for spinning black hole we use the Mukhopadhyay 2002 potential. The energy equation basically taking care, since we have optically thin region, that means ion-electron coupling will be not high, so it will not be thermalized. So we have to take care that two temperature flow. First equation for ion and the second for electron. So this is nothing but first law of thermodynamics. Left hand side basically telling that entropy gradient, and Q plus is the magnetic or viscous dissipation. Since ion is much heavier than electron, so whatever heat will dissipate, it will go initially to ion. It will couple to electron through this Coulomb coupling, and that Coulomb coupling, electron will get the heat and it will radiate through different cooling mechanisms like Bremsstrahlung, synchrotron, and inverse Compton process. And following the Chandrasekhar model, we write down that entropy gradient in terms of gas radiation mixture, where the gamma 1, gamma 3 is basically telling that adiabatic indices, which is written in terms of beta and plasma beta parameter. Since we have magnetic field in the system, so the disk we have to solve self-consistently the no magnetic monopole condition and also the induction equation. So if we couple all the equations, so we can write down the velocity gradient in terms of some numerator by denominator which has non-derivative term. And since the black hole accretion is transonic nature, that means it has to matter from subsonic to supersonic. It has to pass some sonic location. So this is known as critical point or sonic point condition, where the denominator and numerator will vanish simultaneously to give smooth solution. So this is one boundary condition in our solution. And we write down the magnetic field in terms of the sound speed of the medium with this constant parameter F. F is the inverse of the magnetic field strength. So it is plotted that inverse of magnetic field strength and different velocity component like radial velocity, sound speed, and Alfvén velocity. So you can see when magnetic field is very weak, like F is very large, so the Mach number is basically 1. That means radial velocity by sound speed is always matching. But as we keep increasing the magnetic field, so after some time, Alfvén velocity will cross that sound speed of the medium. So after that, this cannot sustain large scale magnetic field, and below that we cannot go that much magnetic field in this disk region. So in our solution, the maximum acceptable magnetic field region in this to get the stable solution. So in this way, we can control magnetic field strength from weak field to high field region, where from large scale magnetic field can advect both for toroidal and toroidal field dominated cases. So to get that ultraluminous X-ray luminosity in the physical nature is, we can see that luminosity versus radius is plotted here along with the magnetic field strength. So you can see that red dotted line is basically telling that Eddington magnetic field limit, where the black dotted line is the magnetic field strength in the disk. So what is Eddington magnetic field? It is basically telling that energy associated with that magnetic field, if we equate with that Eddington luminosity, then we can get that Eddington magnetic field at each and every radius of the disk. So this is plotted the red dotted line. Now you can see that when the large scale magnetic field supply from external component star is large enough compared to that Eddington field, so it can give very large luminosity even for stellar mass black hole and sub-Eddington accretion rate. By keeping everything same, if the magnetic field supply is less than the Eddington magnetic field limit, the luminosity will also be very less, and as we expect from the conventional accretion process, where that gravitational energy only released as the heat or radiation. So what is the explanation of large luminosity? What is the source of energy, and how this radiation pressure will hold in the system? So how magnetic field play the role here? So here you can see the large luminosity 6.610 to 39 hour per second for stellar mass black hole and sub-Eddington accretion rate. So the maximum gravitational energy you can see 910 to the 38 hour per second. This is available energy. But maximum magnetic energy, if it is supply from the component star is large enough, So it can be supplied like 8×10⁻39 arc per second. So as the disk magnetic energy is dissipated and cooled down through synchrotron and synchrotron self-configuration process, so the disk luminosity will increase and it will saturate after the region where magnetic field will not give enough radiation. So in this region, gravity will take care, and after that, magnetic field can also increase a little bit by conversion from gravity. So due to the flux freezing mechanism. Now to large luminosity also can be hold, the radiation pressure will be very high. So to hold that large radiation pressure, here we try to explain that force per unit mass or different acceleration term with respect to the radius. Radius is written in unit of gravitational radius. So you can see different force balance equation is basically taking care gas pressure and radiation pressure. You can see outside that this is zoom version of this region. So you can see the radiation pressure is very high, where gravity even cannot alone sustain that high radiation pressure to explain large luminosity. Rather, the magnetic field has dual nature. One is magnetic tension and magnetic pressure can hold the large luminosity to explain that ULX luminosity in this zone by taking care about stellar mass black hole and sub-Eddington accretion rate. So if I summarize that these things, so ULX in their hard states are basically magnetically powered around the stellar mass black hole, and no need to incorporate the existing or missing class of intermediate mass black hole scenario. So we are not taking care about that intermediate mass black hole scenario exists or not. We are not going in this disputed things. But stellar mass black hole, when large scale magnetic field will be supplied from companion star, so it strongly depends on the companion star idea. So if companion star can supply the large magnetic field, then only it can explain large luminosity. So that's why this kind of ULX are very rare in the nature. So we see around 10 to 12 sources out of 300 sources. And other important thing is that the advection of both poloidal and toroidal magnetic field is happening here, not like the purely vertical poloidal field as happening in the magnetically arrested disk model. So for more technical details, the interested one can follow these two references. And thank you.
Okay, there was a problem with my internet connection. So you finished the talk as far as I understand.
Hello.
Hello. So please, questions, comments.
May I have a question? Recently, the highly magnetized neutron stars were found in some ULX sources. So how can you distinguish your model observationally from the model with the highly magnetized neutron star?
Right. So this is very interesting question actually. So this is very puzzling thing that neutron star or black hole is sitting at the central object is as in ULX. So the thing is that neutron star has some different advantage. Like if we see the pulsation, then we can confirm this is neutron star. Now neutron star has extra advantage because of its high magnetic field. So all we know that the Eddington luminosity limit itself is inversely proportional to the scattering cross section. So when magnetic field is very high, so the scattering cross section will be suppressed. That means that it will extend that Eddington luminosity and it can give very large luminosity even for the same accretion rate as in black hole. At the same time, since neutron star has large magnetic field, so the accretion will be halted and like channel flow will happen. So radiation can come out like fan beam or radiation beam type pattern. So that means the radiation pressure will not balance by the gravity. Again, it will balance by the magnetic pressure. So these two advantages neutron star has compared to the black hole. So that's why we try to explain only up to the 6×10⁻39 arc per second, as we see. But neutron star can easily go up to 10⁻41 arc per second, which we observe very few, like 7 or 8 neutron star ULXs. So yeah.
Okay, thank you.
Okay. Yes, please.
Yeah. Can I have a related comment?
Yes, please.
I am Banibrata, his co-author. Actually, Here, one of the main targets is to explain high luminosity, but in the low Hard state. The neutron star source, what you are talking about, I don't remember. Do you remember the underlying spectrum, whether it is in the hard state or soft state? If it is in the soft state, then again problem remains. Like our problem remains there. Okay, it can be explained by high accretion rate or whatever he explained. But problem is, even if like the sources he considered, system is in the hard state, which is presumably low luminous, the general idea. But still, observationally, we find luminosity high. How to explain? That is why he considered strong field, but in the hard state based model. So that is the main kind of take home I can say here, that how to extract high luminosity in the hard state system. The neutron star source, in my understanding, it may not be in the hard state, but you may correct me.
Okay, thank you. The next question, Evgeny Mikhailov, please.
I would like to ask you if the equations that are solved are stationary and you don't describe the magnetic fields and velocity fields which depend on time.
So in the soft state you are talking about, basically the like very high state some ULXs we see. So very high state means we can see the power law plus some black body type kind of spectra. So in that cases, again, that advection also dominate because of super Eddington accretion is happening. So that can easily explain large ULX luminosity even for advection also operating. But the thing is that we don't require for like stellar intermediate mass black hole scenario, but stellar mass black hole can easily explain that. But the thing is that what we explain here, that only hard state sources where the photon index keep fixing constant, but the luminosity is varying one order larger, and still it's like not low hard state, but it's telling that bright hard state type spectra. So that's why the large scale magnetic field is advection is required here to explain that large energy budget. Is that your question?
Thank you. To my mind, yes, I have understood.
Okay, let's thank our second speaker. So we a little bit beyond the time limit. So please stop sharing your screen. And the next talk will be given by Maria Glushihina. Calculation of the tensor components of the kinetic coefficients of arbitrary degenerate electrons in the neutron star crust. Maria, please start sharing your screen. Okay, good. Yes. And switch on your microphone. Please, okay? Yes. We see you and we hear
you.
you.
Do you hear me?
Yes, we hear and see your presentation. Please start.
One moment. How to do it? I can full mode.
Full screen of your presentation.
Yep.
Needed.
Okay.
Yes, it's good now.
Do you see it in the full screen?
Right.
Okay.
Yes. Start,
so good morning. It's rather early morning in Russia. So my talk is about kinetic properties of neutron star crust, and we do this task because we want to investigate temperature distribution on the some of the isolated magnetized neutron stars. Because X-ray observations of thermal emission show periodic variabilities in single magnetized neutron stars, and it indicates to the isotropic temperature distribution. So if we study temperature distribution, maybe we can see the magnetic field distribution on the neutron star crust, and maybe we can understand the geometry of magnetic field and on the neutron star surface, and as far as we can deep in the neutron star crust. These objects then that we use, they often called Magnificent Seven. And among all thermally emitting neutron stars, Magnificent Seven are the only ones with a purely black body spectrum. The clean thermal emission is unmarred by contaminations from magnetospheric activity surrounding nebula or supernova remnant. And for analysis of the emission, we need to know the transport properties of the crust, and we assume that the matter of the crust consists of degenerate electrons in the Fermi gas form and from non-degenerate nuclei that form Coulomb liquid or Coulomb crystal. So we can say that electrons are the main heat and charge carriers under such conditions, and kinetic coefficients are determined mainly by the scattering of electrons by ions. And in the majority of works, considering the diffusion and heat conductivities in the astrophysical objects, the influence of magnetic field on the heat and electroconductivity along the cross magnetic field lines was taken like in these ratios. Can you hear? Can you see the my tripod? Yes.
Yes, we see.
The sign. Okay. Like this, and here is a ratio of electroconductivity across magnetic field lines to the electroconductivity along magnetic field lines, and here is for heat conductivity, and it shows us the rate of magnetic field influence. And the first ratio was introduced by Flowers Ito in 1976, and the second one was introduced by Yakovlev and Urpin in 1980. And these ratios both were obtained as estimations with using mean free path theory. And in our work, we calculated all sets of kinetic coefficients, namely heat conductivity, diffusion, diffusional thermal effect, and thermal diffusion, by solving Boltzmann equation. We considered two cases. For arbitrary degeneracy, we solved Boltzmann equation by Chapman and Scott method of successive approximations, and we solved Boltzmann equation in Lorentz approximation for the case of strong degeneracy. Chapman and Scott method is used when the distribution function are close to the values in thermodynamic equilibrium, and deviation is considered small. And for successive approximation method, we use the first three polynomials that analogous to Sanin polynomials, Sanin-Laguerre polynomials. And here you can see the first three polynomials that we used. The G here is a Fermi integral, and X0 is the ratio between mu, that is chemical potential, and temperature. Lorentz approximation is applicable for solving a kinetic equation when the mass of light particle is much less than the mass of a heavy particle, and in our case we can neglect electron-electron conditions, and the Boltzmann equation has an exact solution in this approximation. And Lorentz approximation is very useful for testing an approximate polynomial solution because we can see the convergence of an approximate solution to the exact one. And here are our results for non-degenerate case. We can see here the plot on the y-axis is a ratio of electroconductivity across magnetic field lines that is calculated from the Boltzmann equation that was solved by polynomial expansion. and electroconductivity along magnetic field lines that was calculated from the Boltzmann equation that was solved in Lorentz approximation. So this quantity is an exact one. And here we can see this ratio as a function of omega tau, where omega is electron cyclotron frequency, tau is a frequency is a time between collisions, and these curves are presented for non-degenerate plasma of different atomic numbers. The solid thin line is plasma of helium that corresponds to Z equals to 2. Dotted line is a carbon plasma. Here it is. And dashed dotted line is iron. And we compare all of them to the Lorentz plasma that's formally corresponding to the Z equals to infinity. And all of these deviations from Lorentz plasma are connected with the input of electron-electron collisions. And we can see that this thick solid line, it doesn't go to the 1 exactly. And this deviation that is less than 1%, it is connected with the polynomial solution, because we don't have enough polynomials to go into the exact exact quantity. And we have the same results for diffusion, for thermal diffusion, and for diffusional thermal effect. Again, for the Lorentz plasma, for the iron, for carbon, and for helium. For partially degenerate electrons, we examine the effect of increasing degeneracy on the convergence of polynomial solution to the exact one. So in order to do it, we compare the coefficients calculated by the method of successive approximation with coefficient obtained as an exact solution Lorentz approximation for different degeneracy, for non-degenerate electrons, and for the level of degeneracy when the chemical potential equals to 0. So we have the following results. When we have this partial degeneracy, when our chemical potential equals to 0, the thermal conductivity differs from exact solution by 13% and thermal diffusion by 7%. But when we calculate it for non-degenerate electrons, thermal conductivity differs from exact solution by 2.2% and thermal diffusion by 1.3%. For partial degeneracy, for diffusion and diffusional thermal effect, we have analogous results. For diffusion differs from exact solution by 2.6%, and diffusional thermal effect differs by 8%. And for non-degenerate case, diffusion and diffusional thermal effect almost coincides with the exact solution. So difference is less than % for both cases. So we can see that accuracy of approximation method decreases when our rate of degeneracy increases. And for strongly degenerate case, we can see that the collision integral for Newton-Newton collisions have been found analytically in the Tamanaga work in 1938, and they were calculated for strongly degenerate neutrons and nuclear matter, and for neutrons in the inner crust of neutron star with many free neutrons. And it was found that the input of neutron-Newton collisions to the kinetic coefficients is negligibly small in comparison with the neutron-nuclei collisions. So we had the same situation when we describe the strongly degenerate electrons. So for strongly degenerate electrons, we can say that Lorentz approximation with a count of collisions between light and heavy particles only is asymptotically exact. So when we solve the Boltzmann equation in this approximation, we have the following results. Here again, the plots of ratio heat conductivity cross magnetic field lines to the heat conductivity along magnetic field lines that were calculated for strong degenerate electrons in Lorentz approximation both. And the solid line corresponds to the phenomenological method that was used by Yakovlev-Urpin. I showed this ratio on one of the previous slides. And our results is a dashed curve. And we can see that in the range from of omega tau from 1 to 1.5, we have 4 times smaller quantities. And for diffusion, we have a different situation. And for diffusion, the curves obtained by the phenomenological method that was used again by Yakovlev and Urpin and Flowers and Nito, they coincides with the solution of Boltzmann equation when electrons are strong degenerate. But if we take into account the small terms in exact solution, so we will see the difference. For different rates of degeneracy. Here is as an example, we put 2 cases of degeneracy when the ratio of chemical potential and temperature is equals to 5. This is a dashed curve. And when the ratio of chemical potential and temperature equals to 9, this dot dashed curve. We have the same exact situation for the diffusional thermal effect, but for thermal diffusion, we have a situation that is analogous to heat conductivity when we see the clear difference from the phenomenological estimation. In the work, we calculated 4 sets of kinetic coefficients for plasma and magnetic field with arbitrary degeneracy by solving Boltzmann equation with Chapman-Scott method of successive approximation, and the influence of degeneracy on the convergence of 3 polynomial solutions to the exact one is considered. And for strong degenerate electrons, the kinetic coefficients are obtained as an asymptotically exact solution of Boltzmann equation Lorentz approximation. And it is shown that the kinetic coefficients that obtained from solution of Boltzmann equation more accurately take into account the influence of magnetic field and kinetic properties of degenerate electrons. That it was done in the previous works that used mean 3-path theorem. And the influence of magnetic field turns out to be stronger and more complex. And these coefficients were used for modeling of temperature distribution on the surface of the neutron star with dipole and quadrupole configuration of magnetic field that was performed by Ilya Kondratyev and Sergei Moiseyenko. Here on the left figure, the angle between axes of dipole and quadrupole magnetic fields is 45 degrees, and on the right figure, the angle between magnetic field axes is 30 degrees. And here we can see the temperature distribution in the crust of the neutron star when the angle between magnetic field axes is 45 degrees. And here is a link on the paper when these simulations were done. So here is it.
Okay, thank you, Maria. Please, questions, comments? Okay, well, people are thinking May I ask you, what are your plans for the future in this field?
In the future, we plan to calculate more precisely I think whole currents on the surface of isolated magnetized neutron star with use of this all sets of all these kinetic coefficients. Maybe we'll do some another modeling.
Thank you. If there are any more questions, comments? Okay. If no, please, Maria, stop sharing your screen. And I'd like to announce the next talk, which will be given by Sabham Ghosh, the origin of hydrodynamic instability from noise in the Keplerian accretion flow and its rivalry with the magnetorotational instability. So, do we have a next speaker, or please share your screen. It's a green button in the lower part of your Zoom screen, Zoom window. Can you hear me?
Yeah, hello, I can hear you. Can you hear me now?
Yes, we hear you. Please share your screen.
Okay, yeah, just a second.
Okay, good. Now we can see your presentation.
You can hear me, right? Clearly?
Right. We hear you and we can see your presentation. Please start.
Okay, thank you. So let's begin. Yeah, good morning, everybody. And I'd like to thank the organizer for giving me this opportunity. I'll be talking about the origin of hydrodynamical instability from noise in the Keplerian disk, Keplerian accretion flow, and its rivalry with the magnetorotational instability. So this work, most of this work got published in Physical Fluid very recently, and it is done with my supervisor Bani Pratap. So observational evidences say that the accretion disks are turbulent, though they are relativistic. By relativistic means, if we consider a local fluid parcel in a accretion disk in Keplerian region, if we perturb this, the perturbation decay. Hence, the local flow is stable. Now, the question arises whether there is any instability mechanism through which the fluid may become turbulent. To answer that, Balbus and Howley in 1991 proposed an idea of coupling between magnetic field and rotation, and through which one instability mechanism arises. It is called magnetorotational instability, following the idea of Velikov and Chandrasekhar. Most in particular for hot disk. Now, I hope how this magnetorotational instability works is well known to this community, so I'm skipping this. Now, over the years, this MRI, magnetorotational instability, has been quite popular and very successful in explaining the accretion phenomenon. However, it is not out of limitations. For example, in protoplanetary disk, where there is low ionization, it got suppressed. Beyond certain toroidal magnetic field, and where there is magnetic field stronger, it ceases to work. So, although in those cases there are different mechanisms to incorporate the instability and hence non-linearity and hence turbulence into the system. However, we look for an hydrodynamical counterpart. That is there any linear instability from hydrodynamical point of view to explain the turbulence? To do so, we follow the recent technique. Lately, the effect of an extra force which is stochastic in nature and delta correlated with non-zero mean. This effect of extra force has been explored in Navier-Stokes equation in the linear perturbation to explain the underlying instability that could further give rise to turbulence. Now, question arises: what could be the plausible origin of extra forces? For example, the interaction between the dust grain and fluid parcel in protoplanetary disks, the feedback from outflows or jets onto the disk, etc. Having said that, let's formulate the problem. We go to a very local region in a accretion disk at a particular radius, and there we consider a Cartesian box. So to incorporate the effect of rotation in at that particular radius, we rotate the box along that radius throughout the disk. And due to the differential rotation inside the Keplerian accretion disk, there will be shear, background shear will get generated inside the box, which is linear. So this is the background flow. This linear shear inside the box is the background flow, and we perturb this linear shear flow, and we see how this perturbation behave. That is, how they evolve in the presence of extra forcing. So we write the governing equation, which are nothing but the Navier-Stokes equation, but in a recast form, because we are dealing with incompressible fluid. So we recast the Navier-Stokes equation by eliminating pressure term into Orr-Sommerfeld and square equation in presence of extra force and Coriolis force. As there is noise involved in the system, we ensemble average these linear Orr-Sommerfeld and square equation. So these one Orr-Sommerfeld and square equation, and these M1, M2 are the mean of the noise. Now, if we consider this M1, M2 to be 0, then this system has been studied for transient growth for linear shear flow by Mukhopadhyay, Afsar Narayan in 2005. Now we solve this equation with the Nosley boundary condition, where, as I mentioned earlier, this U is the capital U is the background shear velocity, and it is linear in x. And this small u and zeta are the x component of perturbed velocity and perturbed vorticity. This q is the rotation parameter, which is 1.5 per Keplerian flow, and the angular frequency at an arbitrary radius scales with the radius as this, that is the relation between angular frequency and radius, where 0 refers to the reference radius. Now we try to solve those equations, where our trials solutions like this. Here alpha is 3-dimensional, and this x vector is 3-dimensional vector, position vector. We try to solve this ux. So along other 3 directions, these are Fourier solutions. This beta is complex usually, and it's the frequency. So its imaginary part, if it is positive, then there is instability in the system. Now with the help of these solutions, the Orr-Sommerfeld square equation after ensemble average, they become like this, where this u0, zeta 0 are these values. I mean, all the zeros are the values at x equals to 0, where this prime in u prime and zeta prime denotes the derivative with respect to x. And so while we derive these equations from the Orr-Sommerfeld equation, we neglect the second and higher order derivatives over as they are varying. The assumption is taken that as they are varying very slowly over this length scale, and we consider this first order derivative following this rule. So with these assumptions, these previous equations can be recast into the dispersion relation. That is how this frequency varies for equal mean of the noise. Now, of course, these coefficients are complex quantities in general, and they are the function of these variables. Now, our target is to see the solution of these, particularly the complex, the imaginary part, how the imaginary part of this beta varies. So let's do that. Check that. So this is the variation, so this is a contour plot. So along x-axis it is the alpha 1 along the wave vector along x-axis, and alpha 3 along plotted along y-axis, which is nothing but the z component of wave vector. Sorry, I got disconnected. Hello?
All this.
Hello? Can you hear me?
We can hear you, yes.
Hello? Can you hear me?
Yes.
Okay. Sorry, I got disconnected. So I was saying that this if there is no noise, then the system, the flow is stable for even for very large Reynolds number. That should be the case. Now, if we introduce the noise, that is, let's consider m by u naught to be 10. Now we see the how the imaginary beta varies for different Reynolds number. We see that here as Reynolds number increases, this domain or range of alpha 1 alpha 3, that gives rise to positive imaginary beta. In left panel here, this is the positive imaginary beta, and here almost throughout the domain it is positive imaginary beta. So it says that as Reynolds number increases, the domain of alpha 1 alpha 3, which gives rise to positive imaginary beta, that increases. Now we plot three-dimensional plots to incorporate how the maximum value of imaginary beta changes as we change the Reynolds number, as we increase the Reynolds number for the same m by u naught. We see that Reynolds number as increases, then the imaginary beta max also increases. So from here 0.8 to 0.9. Apart from that, it is also clear here the domains are same of alpha and alpha 3, and we see that this positive imaginary beta within the range of alpha and alpha 3 is smaller. I mean, the range of alpha and alpha 3 is smaller, that gives rise to positive imaginary beta. But here it's within the almost throughout the domain, the imaginary beta is positive. So from this dimensional plot, we verify these two claims. Now, if we increase m by u naught for a fixed Reynolds number, we see that the maximum value of positive imaginary beta increases. For example, here the maximum value of imaginary beta is 1, but here it is more than 2. So with the increase of m by u naught, the positive imaginary beta value increases for a fixed Reynolds number. So let's plot these imaginary beta maximum values for different as a function of Reynolds number. What we see that for a particular m by u naught, it increases and then gets saturated. And if we increase these m by u naught values, that is the strength of noise, then this saturated value also increases. So it is also interesting to study the dependence of the maximum growth rate on the strength of the noise, this m by u naught. We see that as the m by u naught increases, the three black, red, and green, these dots represents different alpha 1 values. We see that as m by u naught increases, the imaginary beta value, maximum value of imaginary beta also increases. And beyond certain value of m by u naught, we see that this distinctive nature of different alpha vanishes. That is, at higher value of m by u naught, the noise, the system almost is controlled by the noise and the Reynolds number only. So let's study the Argon diagram. So what is its significance will be clear as we go along. Now the temporal variation of the perturbation is like this. It has exponential temporal dependence. Depending on the values of imaginary beta, if it is positive or negative, it will grow or decay, and it has also the oscillatory dependence whose frequency is this real part of beta. Now we see that as so this plot shows the along y-axis it is the imaginary part of beta, along x-axis it is the real beta, that is why it is Argon diagram. And for this particular parameters, it shows that as alpha 1 values decreases, the maximum value of imaginary beta also decreases. Okay, and the maximum value of real beta, we define this quantity as where the real beta is maximum. So for this example here, it is the kind of real beta, maximum real beta. We see that maximum real beta also decreases as we decrease, maximum real beta decreases as we increase alpha 1. So for smaller alpha 1, therefore, the system becomes unstable at smaller time and plausibly becomes turbulent for those alpha 1 first. Now, alpha 1 equals to 10, we see the real beta max is this value 0.3. Now, what is the importance of this alpha equals to 10? So the perturbation, maximum wavelength of the perturbation should be well inside the box. So it is therefore necessary to have the maximum wavelength of the perturbation to be equal to the size of the box. So the maximum wavelength of the perturbation along x direction is 2 pi by alpha 1 in dimensionless unit. To make it dimension full, we have to multiply this with the size of the box. So we consider those alpha 1 which are greater than 2 pi to describe or to capture the base dynamics inside of the fluid inside the box. That is why we consider alpha 1 equals to 10. And let's study the various time scale. What are the importance of time scale? This confirms our applicability, the applicability of our theory. So, for example, the time that fluid takes to reach the innermost stable circular orbit, that is 3s, from, let's consider the fluid as at 100 solar radius. For a 10 solar mass accretor, it takes almost 8,000 seconds if the saturation and viscosity parameter is 0.1. Now, I mentioned earlier that real beta maximum is the frequency at which the perturbation oscillates. Now, the time period corresponding is this one with multiplied by this is second. I mean, this one is time dimensionless quantity. We multiply this to make it a dimension full unit. So we can for alpha 1 equals to 10, we see that this time period becomes almost 2 seconds, which is very much smaller than the infill time scale. Now there is another important time scale that the fluid parcel takes to cross the box along the radial direction, and it is 5.34 seconds for 0.05 solar cell radius of the size of the box, and if the box is situated at 100 solar cell radius. So we see that this time scale is also very much greater than the time period of the temporal oscillation of the perturbation. Now there is another important time scale, which is almost the when the energy becomes perturbation reaches the nonlinearity. We define the nonlinearity through this this is the expression of these plots are energy as they are the quadratic in velocity, perturbation velocity. We consider this point 10 to the power 4 to be the limit of linearity, and we see that for alpha 1 equals to 10, which is important in our case, is that it reaches the limit of nonlinearity around 10 at t equals to 9, which is 0.8 seconds in dimension full unit, and that is very much smaller than the time that the fluid takes to cross the searing box, which is 5.34 seconds. So the fluid gets enough time to become unstable and nonlinear, and hence become turbulent inside the box. Now, having said that, let's check the effect of magnetic field. So, as I mentioned earlier, these two are the these two are the orthogonal equation, but here there will be the magnetic version because of the low range force, and these two equation arises because of the presence of induction equation, where this Bx is the x component of perturbation and zeta b is the x component of part of the magnetic vorticity, while background magnetic field, this B0 is defined like this for the simplistic case. Now, with this help of this equation, we will arrive at the dispersion relation, where the solutions like this are like this, where zeta can be any of these 4 variables, u zeta, velocity, vorticity, and magnetic perturbation, and X component magnetic perturbation, and this magnetic vorticity. We consider very simplistic case, perturbation along z direction, and also a magnetic field along the background magnetic field along z direction. Now we arrive at this dispersion relation, where this equation, from this equation we arrive at this dispersion relation, which is quartic in frequency. Now if we study, we see that I am just a couple of slides up there, so I'm almost done. We see that this is a typical MRI without noise. Along x-axis it is magnetic z component of magnetic field, background magnetic field, and along y-axis it is the imaginary part of beta. We see that as the magnitude of magnetic field increases, imaginary beta increases, and it reaches a value of 0.5, and then also decreases.
Excuse me.
Beyond certain value of magnetic field, there is no instability in the system. And also, if alpha 3s, the vectors are increased, the domain that gives rise to positive imaginary beta, that also shrinks. So, for example, for alpha 3 to be 10, the window of positive imaginary beta, the window of B0Z that gives positive imaginary beta is from minus 0.5 to plus 0.5.
Time almost expired.
Now, if we consider this case and take into account the effect of noise, then we see. So these are again the contour plot, where the contours are for imaginary beta, and this B0Z is along x-axis, y-axis, and m by unit along x-axis. We see for this smaller B0Z, here B0Z is valid for 0.5 to minus 0.5. We see that here the effect, the imaginary beta almost follows the MRI, how it varies when there is purely magnetic field, no noise.
Shubham, your time is over.
If the strength of noise increases, the dependence of noise increases little bit, but almost it is dominated by this effect of magnetic field, that is MRI still dominates. But if the magnetic field is increased, for example, here from minus 10 to 10, and here from minus 50 to 50, then we see that the dominance of the noise over the magnetic field increases. And here at the extreme right plot, where the magnetic field is quite larger, we see it is almost there is almost no dependence of on the magnetic field. They are always very dependent on the effect of noise.
Please.
So let's conclude it. So without magnetic field, what we get is that local Keplerian flow becomes unstable due to the very presence of the noise with non-zero mean, and the fluid parcel inside the shearing box gets enough time to enter into the nonlinearism. Hence, the flow further could become turbulent. Once the instability and therefore turbulence kick in inside the shearing box, we consider the shearing box repeatedly throughout the radial extension of the accretion disk, and hence the transport of the angular momentum can be interpreted in the Keplerian accretion disk. With magnetic field, in the weak magnetic field regime, where MRI is active, it dominates over the instability arising due to the noise. But in the strong magnetic field regime, where MRI is inactive, the instability arising due to the noise dominates over MRI. Thank you.
Okay, thank you. I'd like to ask all future speakers, respect the time of your talk. Please remain in 20 minutes.
Hello?
Can you hear me?
Shubham, session chair repeatedly asked you to, shorten and reminded you time.
Oh.
You are not able to hear. You please be careful.
Okay.
At least 5 minutes before, Professor Mashenko warned you.
Okay. Thank you for your help. So we have time for very short question, if there are any, please. If no, then we have a break now. For 10
I cannot
minutes.
hear. I don't know what is the problem.
Can you hear me? So we have.
I think he has some hearing. That headphone problem. I think.
Hello.
I'm sorry for that.
Probably yes. Probably you have a problem with headphones.
Yes.
Okay, good. So we have a break for 10 minutes. So we start our second part of our session 5 minutes later, then in the schedule we start at 5 minutes past 8. So we have 10-minute break. Relax, please. So, colleagues, let's start. So, the next talk will be given by Olga Toropina, and the title of the talk, Magnetized Neutron Stars Propagating Through the Non-Uniform Interstellar Media. So please, Olga, start. 15 minutes plus 5 minutes for the questions and discussion.
Can you hear me? Oh,
yes, we hear you and we see your presentation.
My work in collaboration with Marina Romanova and Richard Lovelace from Cornell University, Ithaca, New York. Many pulsars and neutron stars propagate through the interstellar medium with supersonic velocities, and their pulsar wind and magnetospheres interact with the interstellar medium, forming bow shocks and magnetotails. Here is a good visual example of the such propagates is Guitar Nebula. This nebula was discovered in 1992 and produced by ordinary neutron stars, these pulsars, which is traveling at extra high speed, about 1600 kilometers per second. The neutron stars leaves behind a tail in the interstellar medium which just look like a guitar. Only at this time and from our point of view in space. Guitar Nebula is about 6,500 light years away in the constellation of Cepheus and occupies about an arc minute in the sky. This corresponds to about 300 years of travel for the neutron stars. This picture demonstrates a head of Guitar Nebula imaged by Hubble Space Telescope in 1994, 2001 to 2006 years. You can see the change in the space traces. This change depends on density of interstellar medium. First picture, and you can see that shape has significant changes. An analysis of optical data shows that a shape of the head in the third observation is beginning to resemble another guitar shape. First, second, and third observation. We suggest that pulsar may be traveling through periodic fluctuation in the interstellar medium. Pulsar wind nebula have been observed via X-ray synchrotron radiation from many sources over many years. Two well-known bow shocks of pulsar wind nebula: the mouse, powered by these pulsars, and nebula powered by these pulsars. X-ray and radio images taken by Kargaltsev and Pavlov. Right panel show radio contours and direction of the magnetic field. The red and blue colors in the left panel correspond to X-ray and radio line respectively. This picture demonstrates pulsar bow shocks in H-alpha lines, the image for these pulsars. This picture is taken by Broadberger and Romani. Pulsar wind nebula has a long tail, and has multiple bumps, like bubbles in Guitar Nebula. Two words about evolution of magnetized neutron stars. Rotating magnetized neutron stars pass through different stages of their evolution. First stage, ejector. When a rapidly rotating stars, magnetized neutron stars, is active as a radio pulsar. The neutron star spins down, moving the wind of magnetic field and relativistic particles from the region of light cylinder and Galvanic radius much larger than light cylinder radius. The next stage, propeller. When neutron star spins down sufficiently and relativistic wind is suppressed by the influent matter until Galvanic radius is greater than accretion radius, the centrifugal force prevents accretion and neutron star rejects all incoming matter. Next stage, neutron star rotates slowly and matter can accrete onto the star surface. And separately stage, georotator, and then neutron stars move fast through the interstellar medium. We consider two main cases. First, when Galvanic radius is less than accretion radius. In this case, a gravitational focusing is important, and matter accumulate around the star and interact with the magnetic field. This is named accretor region. And second case, Galvanic radius, magnetic radius is greater than accretion radius, and matter from interstellar medium interacts directly with the star's magnetosphere. A gravitational focusing is not important, and this is correspond to georotator regime. A ratio between Galvanic radius and accretion radius depends on magnetic field of the star and velocity of the star, or Mach number correspondingly density of interstellar medium. So shape of the bow shock depends on density and temperature of the interstellar medium. Yes, first case and second case. We consider an equation system for resistive magnetic hydrodynamic, Landau and Lifshitz. We use non-relativistic axisymmetric resistive MHD code. The code incorporated the method of local iteration and flux-corrected transport. This code was developed by Zhukov, Zabrodin, and Feodoritova from Keldysh Applied Mathematics Institute. The equation of state for an ideal gas with gamma equal 5/3 is the specific heat ratio, and energy of this is the specific internal energy of the gas. The equation incorporates Ohm's law when sigma is an electric conductivity. We assume axisymmetry, but calculate all three components of velocity and magnetic field. We use a vector potential A, so that the magnetic field B is equal divergence vector potential, and this is automatically satisfied to condition number B is equal 0. We use a cylindrical inertial coordinate system with the z-axis parallel to star dipole moment and rotation axis. The magnetic field of the star is taken to be aligned with dipole with vector potential equal this. We consider after reduction to our equation system to dimensionless form, the MHD equation will involve dimensionless parameter, beta magnetic parameter, and eta. Here, on this picture, you can see simulation geometry of simulation region, cylindrical inertial coordinate system with arrangement at the star center. Z-axis is parallel to velocity at magnetic moment, supersonic and flow with Mach number m from this right boundary. Incoming matter is assumed to be unmagnetized. Magnetic field of the star is dipole. We use a uniform grid, approximately this size. The size is different. First, example of moving neutron star in the uniform interstellar medium. Simulation of propagation of magnetized neutron star at Mach number is equal 6. Here's gravitational focusing is not important, and magnetic field are stretched by the flow and forms long magnetotile. Movie is absent. I can understand the reason, but by movie, not sure. On this picture, you can see simulation of propagation of magnetized neutron star at larger Mach number. Mach number is equal 10. Gravitational focusing is not important. This picture corresponds to J-rotator regime. Result of simulation, you can see poloidal magnetic field and vector velocity. Background represent is logarithm density. You can see the bow shock is narrow, and magnetic field aligned, stretched by the flow, and forms long magnetotails. Skip the movie. You can see the tail density and field variation of different Mach number. Density is in the magnetic tail is low, and magnetic field in the magnetic tail reduced gradually. Then this next step, we use non-uniform interstellar medium. We already have the simulation of propagation for magnetized neutron star with Mach number 6 in uniform interstellar medium, and we can take this result of the simulation as a starting point for investigation of the non-uniform interstellar medium. We change a density of incoming matter and observed a variation of the bow shock and magnetic field lines. Let's see. Dense cloud of the interstellar medium pass through our magnetotile. You can see variation of the density of the flow. On this picture, you can see variation of the temperature of the flow. We change a density of incoming matter and observe variation of the bow shock and magnetic field line. Here's logarithm of density across radius, across magnetic tail, and here is logarithm of temperature across the magnetic tail. Next, we try modeling pulsar-wind nebula around pulsars. As the first step, we studied pulsar-wind nebula in the case when pulsar has zero velocity. A pulsar wind represents the relativistic flow of particles and predominantly azimuthal magnetic field. The wind originated at the light cylinder and propagates to much large distances when it interacts with supernova remnant or with the interstellar medium. In our study, we are interested in the external part of the wind, which interacts with the interstellar medium. Then is why we suggest that a neutron star and light cylinder are located deeply inside our inner boundary, our numerical star, and we model only the external region of pulsar-wind nebula. The star has a dipole magnetic field. The axis of dipole is aligned to with symmetry axis. Kinetic energy of matter flow from the ring is higher than the magnetic energy, so that magnetic field is stretched out by the blown wind. Our wind is non-relativistic. Experiments with different velocities and densities in the wind have shown that modeled pulsar with nebula has similar characteristics between the cases with very low density and high velocity wind and another high density and low velocity wind with the same kinetic energy. We choose the second approximation because in the magnetic hydrodynamic simulation are much longer in the presence of low densities. We choose Mach number is 50 and density equal 1. Our next model. We varied the magnetic field at the surface of the numerical star to obtain different levels of magnetization in the wind. We measure the magnetization in the flow using the non-relativistic version of sigma. Here's P is local gas pressure. We investigate pulsar with nebula, which have different levels of magnetization. Here's the example. For non-moving pulsar, distribution of density and pallidal field in the wind around non-moving pulsar. In the case of B equal 1 and 5, magnetic field. 0 is proportional magnetic flux. Left panel background represent then logarithm density, and right panel background is represents a logarithm of sigma magnetization. As the next step, we investigate propagation of this pulsar with nebula first time in the uniform interstellar medium in constant density. Here is example a shock wave what forms around pulsar with nebula with low magnetization, low sigma. Background represent logarithm density. Solid lane represent magnetic field lines. You can see termination shock and bow shocks, and constant CD is constant discontinuity. Right now represents the same, but background shows logarithm sigma, logarithm of magnetization. This is the same case, but for different magnetization level, much large. Here is example of previous model, propagation through the large cloud density with density is equal 3 initial density. You can see the change in density and change in magnetization level. Here, as you can see, distribution of different parameters across the bow shock at level 0 is 1. Density, sigma, and magnetic field. Here is another example with different level of magnetization, propagation of the pulsar with nebula through the large cloud density in the same level of density, but magnetization three times larger than in previous case. And this movie is good.
Olga, you have few minutes left.
Yes, thank you. You can see different parameters for 3 different models. This model differ by magnetic field. Magnetic field 1, 0.1, 1, and 3. So different levels of magnetization. You can see differences, some difference between distribution of the density and distribution of sigma magnetization for 3 different cases. Next, at the next step, we investigate the propagation of magnetized pulsar-wind nebula through the non-uniform interstellar medium, but we investigate interaction Bow shock with small-scale clouds of the maximum density equals 3. You can see small clouds, and our form of our bow shock and magnetotile has different bumps. It looks like a guitar nebula and look like the picture Brauberger and Romano. And next step, we try model pulsar with nebula propagation around cloud with different gradients of density. Here is the Mach number of the star is equal 50. Density of the cloud has positive gradient in that direction. Up to middle of the cloud, and the negative density gradient at the larger distances, and maximum density in cloud increase with the density gradient and correspond to cloud different levels of the density 1, 2, 3 with gradient. You can see that shape of the bow shock and shape of magnetotiles changes with the correspond to changes in sorry, the change in the density. Here is background represent density without logarithm.
Please come to conclusions.
So,
Thank you.
Thank you for attention. Sorry for long talk.
Okay, thank you. We have time for short, or I would say even very short question, if any. Okay. If no, we continue. Olga, please stop sharing your screen. Okay, good. And the next talk will be given by Jean Memen, geometrically thick tori around compact object with a quadruple moment. Good morning.
I will share my screen.
Okay, please start. We hear you and we see your presentation.
Perfect. Welcome everyone, and thanks for having me today. I want to talk about geometrically thick accretion tori around compact objects with a quadruple moment, recently published in Classical and Quantum Gravity. And for that, I want to first quickly talk about the theory, especially on fluids in circular motion, the specific angular momentum, and circular geodesics. In this talk, I wanna discuss the accretion tori model for 2 quadrupolar spacetimes, the Q metric found by Quevedo, the simplest one, and the Eros-Rosen spacetime, the first found quadrupolar spacetime. And both spacetimes are static and axially symmetric. Thus, we can describe the time component of the fall velocity of those fluids by the specific angular momentum, and thus can describe the Euler equation for a perfect fluid in circular motion, as is well known. For a barotropic fluid, those surfaces of constant L and omega coincide. And if then dl is not 0, the differential of the specific angular momentum, then omega must be a function of L, which is known as the relativistic Uncycle theorem. Well, in that case, we can integrate this Euler equation to find this, where W is the effective potential, and which is described as here, where W in is an integration constant, usually set as the effective potential at the inner edge of the torus. And if we then choose constant angular momentum, this integral drops. And if we then choose the integration constant to be this value, this equation reduces to the known value of the effective potential in static and axially symmetric spacetimes depending on the time and phi component of the metric only and the specific angular momentum. Accretion tori that are constructed this way are historically known as Polish donut models. And for them, it's important to study the properties of circular geodesics in this considered spacetimes, as the fluids elements at the center move along circular timeline geodesics. We only consider geodesics in the equatorial plane. For this, we can write down the Lagrangian, the constants of motion, as are well known, where epsilon is equal to 0 for light-like and epsilon is equal to 1 for time-like geodesics. We can define an effective potential, which looks very similar to the Schwarzschild case we all know. And for circular motion, this movement is equivalent to these two equations, where for light-like geodesics, epsilon equal to 0, these two are equivalent to these two equations, where the last one, which is important, gives the position of the photon circle. For time-like geodesics, the two conditions lead to the Keplerian constants of motions, where we can then define a Keplerian specific angular momentum, KSAM, and angular velocity, which are just the fraction of both. And thus, we can calculate the marginally stable circular orbit, or the last stable circular orbit coming from infinity, as the position of the extrema of LK, and the marginally bound circular orbit can be described by EK, the position on where EK squared is equal to 1. And now I want to quickly talk about the two considered spacetimes. The first spacetime is the Q metric, the simplest exact synthetic exterior solution of the vacuum field equations with a non-vanishing quadrupole moment. The metric itself looks rather handy, actually, where Q is the quadrupole parameter, which for Q equal to 0, it reduces to Schwarzschild. It is asymptotically flat, which is important for the definition of the mass multiple moments. And for M equal to 0, it's flat. We can write down the mass multiple moments in terms of Q and M, but for later comparison with the Eros-Rosen spacetimes and the accretion tori in this case, we want to express the Q metric in terms of the physical quantities of M0 and M2, the mass monopole and quadrupole moment, where we restrict ourselves to Q greater than minus 0 and M greater than 0, which is due to the fact that M itself is a mass parameter and does not have to be bound to M greater than 0, but it's equivalent. In this case, we can see that we can describe M and Q in terms of the fraction M2 over M0 cubed, where we also can see that Q is bounded by M0 over M2 over M0 cubed equal to minus 1/3, where Q goes to plus infinity, which is kept to be in mind for the position of the circular orbits. For time, we then compute the position of the orbits. For light-like geodesics, there's exactly one solution for the photon circles, where we can see here that for sufficiently small Q values, there's no photon circle covering the naked singularity anymore, which I forgot to mention. This Q metric itself is describing a black hole only for the case of Q equal to 0. For any other case, it's a naked singularity at R equal to 2M. We can see that for Q smaller than minus 0.5, there's no photon circle covering the naked singularity anymore. We have up to one marginally bound circular orbit, which can only be calculated numerically, but there are up to two stable marginally stable circular orbits, and the root itself splits the family of Q metrics into three classes, where, in short, the class 1 spacetimes include the Schwarzschild case coming from plus infinity to minus 1/2 for the values of Q, where we have one photon circle, one marginally stable, and one marginally bound circular orbit, which is known. The class 2 spacetimes differ significantly, as there are no photon circles anymore in this case, but there are two marginally stable circular orbits and up to one marginally bound circular orbit. For class 3, all the orbits that are in principle there are greater than 2m and are stable. Here we can see the position of the orbits in the Q metric, and we can see that first up for m2 over m0 cubed equal to -1/3, this breaks off, as I told you before, which results in Q going to plus infinity. We can see that the photon circle, the black dotted line, drops below the horizon at m2 over m cubed equal to 1. And at this point, for higher m2 over m0 cubed, we have two marginally stable circular orbits, and the marginally bound circular orbit drops off at about 1.13. When we then calculate the effective potential in the equatorial plane, we can see that the first three cases are the effective potential for class 1 spacetimes. We can see in general they are qualitatively similar. We can see that they have one local maximum, one local minimum. The fluid itself in these donuts, in this Polish donuts model, can take any area that is shaded in here, where the maximal area that's the fluid can take is bounded by the rho slope of this tori, which is indicated by this faint dashed line here. Any fluid we would drop onto the onto this torus, onto this donut, would spill onto the compact object and accrete onto it, which would lower than the amount of fluid there is, and this is the last closed orbit. We can see that for class 2 spacetimes, however, the effective potential goes to plus infinity when reaching the naked singularity. Thus, we have two centers here, and we could, in principle, raise our dashed bar up to 0. Thus, we can construct double tori in this case, which take a quite peculiar form because they look like fish, like I drew them in kindergarten, right? We can see we can either construct one torus with two centers here, or we can construct touching double tori here. This take this form, or we can take physically distinct, physically separated tori in this case. Now let's talk about the Arrest-Rosen spacetime, which is the first found solution of Einstein's vacuum field equations that is identified as describing gravitational field of a central object with a crust moment, which looks quite a bit more unhandy. In fact, as P and Q are the Legendre polynomials of first and second kind in X and Y. And again, we have Q as a quadrupole parameter. Again, this is asymptotically flat. It is flat for m equal to 0. We have the Schwarzschild limit for Q equal to 0. And again, it describes the naked singularity for any other value of Q that is not 0. We can transform it into Schwarzschild-like coordinates via simple coordinate transformation. And we can see that the multiple moments in this case are not bounded like any value of -1/3, as I told you before. They are nice all around. Now let's have a quick look at the orbits, where we can see that for light-like geodesics, there are up to 2 solutions for the photon circles determined by this equation. And we have, again, only up to 1 marginally bound circular orbit. This can only be done numerically. And again, we have up to 2 marginally stable circular orbits, which also in this case can only be done numerically. Again. These orbit properties divide the Arrest-Rosen spacetimes into 3 with a subdivision in class 2, where in class 1, this is equivalent to class 1 Q metrics. And this in orbit properties is similar to the Schwarzschild case, where we have again 1 photon circle, we have 1 marginally stable and 1 marginally bound circular orbit, while in class 2A, we have now 2 photon circles covering the naked singularity. This is quite different than the class 2 spacetimes in the Q metric, but class 2B, however, is again the case where we have no photon circle covering the naked singularity anymore, but 2 marginally stable circular orbits and up to 1 marginally bound circular orbit. Again, we have in class 3 spacetimes where there's no marginally bound, marginally stable, or photon circle anymore, and all orbits here are stable. If we then plot the orbits in this case, we can see that this blue shaded area is the area where we have 2 photon circles. An unstable photon circle, as we know in typical theory, and a stable photon circle right below that. We can see that after this region, we have no photon circle anymore, and again, we have 2 marginally stable orbits in this case, and up to 1 marginally bound circular orbit. If we then construct the effective potential for this Polish donuts, we can see again, the top 3 are class 1 spacetimes, where they are qualitatively similar, which is really more easy to see in this case. And again, we have in class 2 spacetimes, the effective potential can be done via the donuts itself have 2 centers again, right here. And we can see that the effective potential goes to plus infinity, and which is physically separated from the horizon, which was not that clear in the Q-metric case, but here we can quite literally see that. And again, we can construct the double center tori, and we can see this fish-like, this Polish fish-like behavior where we have, we can construct the double tori either by touching double tori with 2 centers, one bigger donut with 2 centers, or physically separated centers. Which brings me to my conclusion that for both the Q-metric and Evers-Rosen spacetime, they can be distinguished via the properties of the circular equatorial geodesics into 3 classes. Where in class 1, the tori are qualitatively similar to the tori in Schwarzschild spacetime, while in class 2, there is in fact qualitative differences where we can construct this double tori, this fish-like structures with the 2 centers, where, however, there's no accretion happening in this case. In class 3, however, which I dropped due to time constraints, the tori itself cannot have a cusp. We only have a local minimum, and there's no accretion happening, which is not of that much importance in the field. So thus, we drop this from the talk today. Thank you.
Okay, thank you very much. Questions, please. Comments. I have a question. Do I understand it correct that you used approximation of barotropic liquid?
Yes.
Yes. So, simply speaking, it means that you neglect the thermodynamical properties, equation of state, and so on. So, what would be your expectations about the shape of the these probably tories or another figures if you take into account the full property, the thermodynamical properties of the liquids, equation of energy, equation of state, and so
on? Actually, we did not. We can have an equation of state for which we can describe the density of this, which we usually do via iso. Let me check the wording before I tell anything that is
you
not...
don't have temperature in the equations.
No, there's no temperature in that equation, that's right. True. And in this case, the tori itself, we also neglected self-gravity, right? And I would suggest that in that case, I'm not sure. I would suggest that they would grow in size, but I did not calculate this this Euler equation with that in mind. Thus, I'm not sure how that would change.
I understand that in this case, the problem becomes much more complicated. Right. Okay, thank you. Any more questions, comments, please? Okay. Thank you again. If no comments and questions, we proceed further. And according to the schedule, the next talk has to be done by Peter Mantias, particle acceleration and high energy emission in the white dwarf binaries RE query and RSCO. But regretfully, I don't see Peter among the participants of our session. I don't know the reason. So for not to waste time, let's continue. Let's hope that Peter will still appear before the end of the session. And the next talk will be given by Maria Pashentsova, modeling of the magnetic fields of accretion disks using NOZ and RZ approximations. Okay, we see your presentation, but we don't hear you.
Hello, good morning.
Yes, now we hear you and see your presentation. Please start.
Yes. Do you see the demonstration of presentation?
Yes, we see.
Yes, we do. Please start.
Thank you. Good morning, ladies and gentlemen. My name is Pashentsova Maria. I'm from Moscow State University Physics Department. Today, the aim of my performance is to shed some light on my scientific work. The title of my presentation is Modeling of Magnetic Fields of Accretion Disks using NOZ and RZ Approximation. It is well-known fact that number of astrophysical objects such as sun, stars, galaxies, and others possesses large-scale magnetic fields. There are reasons to believe that the large-scale magnetic fields are also present in accretion disks formed by massive objects. For their observational study, various manifestations of magnetism are used, such as Z-minor effect, the Faraday rotation of the plane of polarization, and others. There are different approaches which try to describe the field generation. Firstly, some authors describe the evolution of the field as a transport of the accreting matter. Also, the magnetic field can be connected with the central objects of the accreting system. But the observational data and theoretical models of the accretion disks gives us an opportunity to say that we can neglect the interplay between the disk and the central body for most cases and explain the magnetic field generation by the dynamo mechanism. The basic principles of the dynamo mechanism are connected with the transition of kinetic energy of turbulent motions to the energy of the magnetic field. The field generation is usually based on two main effects. Firstly, the celestial bodies or their parts rotate with changing angular velocities that is connected with the rotation and stretching of the magnetic field. Secondly, there are turbulent motions, and their vorticity describes the alpha effect, which is connected with the rotation of the field line. Joint action of these two effects cause the field amplification, which competes with the dissipation effects, which destroy the regular structures of the magnetic field. So, the dynamo is a threshold process. The magnetic field can be generated only if the alpha effect and differential rotation are enough to suppress the dissipation. In this case, it grows according to exponential law, otherwise the magnetic field decays. The generation of magnetic field is described using the Sherman-Krauser-Redley equation, or mean field equation. This equation is three-dimensional, and its explicit solution is rather difficult. For this reason, specific representations are used for each type of object. The accretion disks surrounding different objects such as neutron stars, black holes, or white dwarfs play an important role in astrophysical processes. It can be expected that the magnetic field in them will be quite similar with the galaxy one. The magnetic field of accretion disk can be formed by the dynamo mechanism in them. Of course, it is possible to use direct numerical simulation to find the magnetic field, but the results of such studies describe the field structure. It is in principle quite similar with the galaxy one. It is expectedly because both the accreting system and the galaxies can be presented as thin disks, where the typical kinematical processes are nearly the same. It is highly important to study the structure of the magnetic field in detail. So, to do that, we can take main approximation which has been done for the galaxies. The galactic dynamo is often described with so-called no-Z approximation, which has been developed for thin disks. In this case, the magnetic field will lie with high accuracy in the plane of the galactic disk. Therefore, their Z components can be neglected. Moreover, it is convenient to assume that the field is axisymmetric. The no-Z approximation can be used to study the magnetic field in accretion disks. And also, it is necessary to take into account that the kinematic parameters of the medium in accretion disks will be fundamentally different. We will be interested in solid disk, but we will not be interested in solid disk, but objects with a sufficient large inner radius. In our assumption, the matter moves throughout the disk in a circle orbits. Its angular velocity omega has a Keplerian value, and it could be expressed by this formula, where m is the mass of the central object or mass of the primary star, and using terminological of binary stars. R is cylindrical polar coordinate corresponding to the distance from the central object. The angular velocity is assumed to be in direction to the crater as a result of the dissipative process. The matter moves also radially with the radial velocity v subscript r. We introduce some dimensionless parameters. R subscript alpha characterizes the alpha effect, a vorticity of the turbulent motions. R subscript omega characterizes differential rotation, and such law is is connected with the usual model for alpha effect, coefficient which is proportional to the angular velocity of the disk and the square turbulent length scale. R subscript and lambda shows the half thickness of the accretion disks and the role of dissipation in the disk plane. Taking into account this assumption, the equations for the magnetic fields in dimensionless form look like this. So, in order to bring our model in more realistic form, we introduce non-linearity in this form. This term is responsible for the dissipation of the magnetic field in the disk plane, and this term is responsible for the fall of the matter into the center. The dynamo effect is characterized by a dynamo number. The dynamo effect is threshold effect. For d more than critical dynamo number, the magnetic field increases exponentially, otherwise it decreases. We can take constant dynamo number in the whole disk or changing one. That means that the field will be characterized by a medium effective value. To model the magnetic field, we can describe different boundary conditions. As for external boundary, they describe the zero derivative for the components of the magnetic field. That means that there is no flow. The magnetic field at the inner boundary is much more interesting. We can describe the zero field condition. We describe no interaction between the central body and the accretion disk. We also try to take the conditions of the zero field derivative at the inner boundary, but the results are nearly the same for this case. The results of comparison of the model with constant dynamo number and the changing one is shown on this slide. we can see the dependence of the magnetic field on the distance to the center of the accretion disk for different cases. For different, for both cases, we take the zero condition in the inner boundary. We can see that for changing dynamo number, and the field is narrow in inner parts of the disk is comparable with the equipartition value, but it decreases quite fast, and in the outer parts it is even smaller than in model with a constant dynamo number. On this graph, we can see the dependence of the magnetic field on the distance to the center of the accretion disk for different inner radius with a zero boundary condition. The boundary conditions influence the magnetic field depending on the position of the inner boundary. So we have tried to model the field for different inner radio values. It can be seen that the magnetic field strongly depends on it. For larger inner radio, the field in the inner part of the disk is smaller. However, the field far from the center doesn't principally depend on it. On this graph, we can see time dependence of the magnetic field for different inner radius with the zero boundary condition. We have also studied the time evolution of the field. We can see that for different inner radio values, we have different time for reaching the stationary value. Unfortunately, no-Z approximations can be used for some objects. There are some special effects which cannot be obtained in no-Z approximations, but we can add that for some cases, even for main parts of the accretion disk, we should describe the vertical structure of the field. For example, we can take the accretion disk with the large half thickness of the disk. All we have to consider, for some objects, we should consider vertical floss convection or other effects. So we constructed the RZ model for the magnetic field of accretion disk. For the magnetic field in the axisymmetric case, we can take this model for the field, whereas the toroidal component of the magnetic field is B, and A is the part of the vector potential which is connected with the poloidal field. If we rewrite the Stern-Krauser-Radley equation for every component and take into account that the poloidal component is much smaller than the toroidal one, and take into account that the actual symmetry, so we can neglect all derivatives with respect to the angular coordinate, we will obtain the following equations. These equations are rewritten in dimensionless form. The distance are measured in the radius of the accretion disk, and time is measured in eta divided in h, where h is the half thickness of the accretion disk. Here are different parameters which describe the dynamo action. R subscript alpha described the alpha effect, and R subscript omega described the differential rotation, and H characterized the disk thickness Z. The magnetic field's growth cannot be infinite, so we should take into account saturation of the field. The magnetic field is measured in the units of equipartition. We use following boundary and inner conditions in simulations. So if we compare these two models, we get a graph like this. The solid line shows the result obtained using the no-Z approximation, and the dashed line shows the result obtained using RZ approximation. As we can see, at the dashed line curves reaches higher values than the solid curve, which may be due to the fact that we take into account new effects associated with the vertical structure of the field in the RZ model. On this slide, we can see a graph of the dependence of the magnetic field on the coordinate r and z. The field maximum is located closer to the inner boundary of the accretion disk. The closer to the edges of the disk, the faster the field decreases. In this slide, we can see time dependence of the magnetic fields for RZ model for different dynamo numbers. So we can see the larger dynamo number, the bigger the equipartition value of the field. So we have shown that the magnetic field in the accretion disk surrounding different massive bodies can grow using the dynamo mechanism. To model it, we used the no-Z approximation, which has been developed to study the field in the accretion disk. The magnetic field models with the constant dynamo number and changing one have been developed. For both of them, it has been shown that the boundary conditions play a principal role in the field evolution and structure. If we take the boundary conditions with zero field on the inner boundary, the field is much smaller than equipartition value. Also, we have studied the magnetic field evolution using the RZ model. The typical field dependencies have been studied. The described model can be used in different problems connected with the accretion disk with large thickness. It gives us an opportunity to study effects that cannot be described using simpler approximations. So we have compared the results of these two models, and RZ's approach seemed to be more useful for most cases. So that's enough for today. Thank you for your attention. If you have any questions, you can ask them.
Thank you, Maria. Please, questions, comments? Okay, while audience is thinking, may I ask you two questions? First, a little bit maybe provocative. When you consider the no-Z approximation, you have actually a completely two-dimensional flow. You neglect any movements and that component of magnetic field. How doesn't it contradicts with the Cowling theorem, which forbids the dynamo development in 2D cases? Or maybe I'm wrong.
You means that I neglect that component, or what
Right.
do you mean?
You neglect that component of the magnetic field, and you also neglect a movement of the matter along the direction. Actually, you have two-dimensional picture of the flow.
I don't think so. I don't think so because we just wait a moment. I haven't this slide on this slide, but we consider that that component is changing according to Cosine's law. So that component is depending on that on a field. Sorry. Yes. Sorry.
Could you please show a slide with 3 or 2 slides later, this one, where the equations for no-Z approximation?
Well, it is, I'm as a co-author can say that we are speaking about the regular magnetic field, which is large scale. Of course, there is some small scale component which can have the Z part, and even the large scale magnetic field can have small Z component, which takes into account, can be taken into account in the equations. Only if we have its Z derivative, and if we take the Z derivative of the Z component, we can replace it by the solenoidality condition of the magnetic field, and so the equations won't have the Z component in explicit form, but it is taken here in non-explicit form.
Mm-hmm. So, and automatically it means that dynamo is not forbidden in this approximation. So that's why you get its development. And my second question is, which method? So actually, you were solving non-stationary problem. You are solving equations, differential equations in partial derivatives. Which method did you use for the solution of these equations? Which numerical method?
Explicit scheme. Explicit scheme.
Just simple explicit scheme, and it was
Yes,
enough.
it was enough because it's very fast to calculate it, and it's very simple. Yes, it was enough for the numerical study.
Thank you. Any more questions, comments, please? Okay, if no, thank you, Maria, again.
Thank you.
Please stop sharing your screen. So among the participants of our session, I still don't see Peter Maintis. So regretfully, we have to finish our session. Let me say thank you very much to every participant and listeners. And let me remind you that there will be proceedings of Marcel Grossman's 16th meeting. So please follow the rules on the site of the conference and take into account the dates when there is deadlines. And for people who took part in the previous Marcel Grossman meeting, which was 3 years ago in Rome, I was told by the organizers that that still proceedings of previous meetings still not appear, but they almost, I would say, almost promise that they will publish soon. And these new proceedings of this current meeting will be published in electronic form and much faster. It's expected that it will be published much faster than it was in previous years. So thank you very much, everybody. So have a good luck, have a good day. Goodbye.